So all of yesterday, we looked at problems of the following type. We said we want to find the minimizer So again, X is our vectorized image that we want to estimate. O are the vectorized observations. And I'm giving the denoising scenario in this case. The first term is our prior. And now there are many ways to generalize this. For example, in conditional Gaussian Markov random fields, we will turn Q into a Q of O. This will somehow depend on the observations. In the fields of experts that we will also talk about today, we will no longer be happy with just having the quadratic form here, but we will want a more general dependency, in particular one that involves more than just tuples of random variables. And finally, and if time permits, I will today talk about trained reaction diffusion processes. This is my favorite paper from CVPR 2 weeks ago. So TRD for trained reaction diffusion. And like the field of expert papers, they touch this functional form, but also change the minimization procedure. And each of these changes makes the model more expressive and more powerful. So yesterday I told you this. What's good about this formula is that it's very simple, and what's bad about it is that it's just a poor model for images. And today we will turn this into a strong model for images. So starting with, I was too fast. So TRD was trained reaction diffusion, FOE was fields of experts. This is just a qualitative overview of what's happening today, yeah? Which parts of the formula we're going to touch today. So the first one, I want to start with conditional Gaussian Markov random fields, or CGMRFs. So we had written an error that was given by X transpose QX, Q the precision matrix, and I already showed a little bit how such a precision matrix can be derived, and I argued in terms of finite differences in the X and Y direction. In general, let's say that we can factorize our precision matrix into F transpose F. And one possibility is to generalize this as follows. So this was Q, and we now want to turn this into a function of the observations. Yes? Yeah, I sometimes put the half and sometimes don't. Okay? And so that was the question, yeah? Now, one possibility to generalize this as follows. I can say I want to have a sum of several of such filters. Note the space that I'm leaving here. I am leaving this space because if I write it like I just did, then, well, the sum of all these Fj transpose Fj's is just going to be another matrix Q. It's just a different factorization. I didn't change anything. So the significant change is that I can now introduce a weight matrix in the middle, and this weight matrix somehow depends on the observations, and Marshall Tupman and his co-authors in work from 2007 and the following years used the following, or proposed the following functional form. As a weight matrix, they used a diagonal matrix which had along its diagonal the following. Let me first write and then I will explain. Okay, so let's look at this element by element. O are the vectorized observations. So O is an n by 1 vector. G is the matrix representation of my kth convolution filter. So this is a circulant matrix. So GK has dimensions n by n, and the result will be a, let me call this an output image. Output image is not good. It's not the original image, but it's the image transformed by some filter. So let me call this transformed input image. So for example, G can be things like smoothing filters, convolution filters, whatever you want, as long as it's a linear operator. The thetas here are weights, and so what we get here is a linear combination of the outputs of a filter bank. Okay, if I sum over parameters k. So this is the weighted output or weighted combination of the output of a filter bank. Weighted combination of the output of a filter bank. Filter bank just means a collection of filters. So we have filters indexed by small k. We have a few of these, and then we somehow combine in a pixel-wise fashion their outputs. And this entire thing is now pushed through a nonlinearity. You could really use, any one that you like. You could have used a sigmoid or something. Here, they've taken the exponential function, because if we want to compute derivatives of this entire energy function, this is going to be convenient. And the whole thing blows it, or not blows it up, well, the diagonal operator just puts this in a big n by n matrix. So what I have now is a weight per pixel, depending on my input image O, on my observed image. And this weight per pixel has an index j because I'm learning a whole set of these to put them into this function here. So the f's, there are plenty of choices here. The particular formulas that I'm using is arbitrary. So for example, as I said, the choice of this specific nonlinearity is arbitrary. And then we have plenty of parameters. So can you, besides the choice of the formalism, can you tell me what parameters we have here? Yeah.
The filters and the rate.
Which filters? The
G.
GK, okay.
And the theta rate.
And the thetas, plenty of them, yeah. And what else? Pick any letter.
Also the F.
Also the F. Okay. Now we can either learn all of these by gradient descent from a training set of denoised images, or we can fix some of them. We could say, for example, for G, I take the Fourier filters, or I take the discrete cosine transform, which is a bit nicer because they're real. I take the discrete cosine transform filters, and so on. Anything you like. So the consequence of this is, so let's maybe start. Let us start, with capital J equals 1. Yeah? So we just want to look at a single. So if I use capital J equals 1, if I omit the W, then I'm back to the formula on the top of this page. Okay, so the difference, the formula on the top of the page, always used for a 2D image. These weights of central, or these entries for a central pixel and the connection to its neighbors. And in applications like the random walker that you've seen, we want to now make this probability of having a random walker transition between two pixels, we now want to make it dependent on the image intensities. This is already something we did many weeks back when we wanted to do the foreground-background segmentation, where we made the cost of a label transition depend on the local image gradient. So let's say if I have a strong edge on the pixel to the right here, then maybe I don't want to enforce smoothness. Maybe I want to make this a 0, and then this here should become a +3. So I don't want to enforce smoothness because I have evidence in my image for there being an edge, so I don't want to over smooth this edge. And to achieve this kind of dependence on the output, I now want a weighting per pixel. And this is what we have accomplished. We have a weighting per pixel, and the weights themselves were some nonlinear function of the noisy image that I have observed. And again, the filters G, they can be something like derivative filters or difference of Gaussians or something that will give me evidence for there being an edge in the vicinity. So this is why we want this matrix W. And now I can use values j larger than 1 because I want even more flexibility. So for example, we used the harmonic operator L so far, but in principle I could say, okay, I want to smooth by having a prior which combines my harmonic operator and the biharmonic operator. And I don't know what this is called, the triharmonic operator. And now the sum of, I can now factorize each one of these. So if L can be factorized as F transpose F, then L squared can be factorized as F transpose F times F transpose F, or something like that. Yeah. So this simply gives me more modeling power. It gives me more flexibility. Overall, I thus obtain a smoothness prior that is no longer uniform over the image, but that tries to avoid smoothing across edges, if I'm talking about denoising. Yeah? So essentially, what this matrix W tries to do, it tries to figure out where in the image, in the denoising case, where there are real edges, because those I want to preserve, and where there are edges that are just, a consequence of the image being noisy, and those kind of high frequencies it wants to suppress. And this distinction between what structures we want to retain and what structures we want to suppress in the image, this distinction is being learned because, and that results in a so-called Bilevel optimization problem, because I can minimize this thing to give me an estimate x star of what my image looks like. And now I want this estimate x star to be as close as possible to the ground truth that I have for my training images. So for image denoising, it's very easy to generate a training set. You simply take high quality images and then you add noise. Okay, and the noise is your input and the high quality image is the output that you're trying to recover. And now we have a bilevel optimization problem in the sense that we are trying, so x star depends on x star that we find depends on the parameters that we have. Yeah, I could add here the parameters explicitly in this energy function. And now we want to find the parameters that will give us an x star as close as possible to our ground truth. And unfortunately, x star is itself the result of an optimization problem. So we have two nested optimization problems, and these are often solved iteratively. Good. So what we have accomplished here overall, we have now a much more expressive model, which now has a precision matrix that depends on the input, but we're still limited in the sense that our MRF is still pairwise. We still have only interactions between two random variables at a time. Okay, and now we will have a break, and after the break we will lift this restriction and we will create Markov random field of continuous variables that involve factors between more than just two random variables at a time. Okay, so fields of experts are next. About the motivation for this. So what's nice about Gaussian conditional random fields is that we need to specify only pairwise interactions. And what's bad about them is that we can only specify pairwise interactions. Okay? And now we want to go beyond this limitation. So we want to achieve not only potentially high connectedness, as we already can with Gaussian, but also we want to go higher order. And as another motivation, I want to mention a fact of life, an empirical fact of life. There are many empirical facts of life, but the one I want to refer to here is that natural image statistics are heavy-tailed, or they follow heavy-tailed distributions. And what I mean by that is shown in this image below. So this figure is from a paper by Krishnan and Fergus from 2009. We see a natural, more or less, image on the left-hand side. And then we can take the gradients, for example, by just taking the finite differences in the horizontal direction, let's say. And then we can make a histogram of how often does any particular finite difference occur. So we have the gradient on this axis and the logarithm of its frequency on the other axis. And then you see first the empirical, this is the dark blue line, which gets a bit wiggly on the extremes. It does get wiggly there because these are very low probabilities, so we didn't have enough examples to get a very smooth estimate. And you also see a few fits to this distribution. Remember, this is on a log scale, so the Gaussian just becomes a parabola pointing downward. This is the cyan. This is a pretty bad fit. Then the red one is a Laplacian distribution. This is less bad. And shown in green is a hyperlaplacian. This is a bit better. And you've probably heard about some of these distributions before, but I want to remind you. So the Gaussian is proportional to that. The student t distribution that depends on the degrees of freedom. So for a single degree of freedom, this is proportional to 1 over 1 plus x squared. And this is also called the Lorentzian or the Cauchy distribution. With 2 degrees of freedom, it is proportional to 1 over 2 plus x squared to the power of 3/2. There is a general formula for new degrees of freedom. Like this. And if you let nu go to infinity, then you again get the Gaussian. And somewhere up there I have a plot of these, which I will just pull down. It's from the boost.org website. So shown here in blue, this is the Gaussian, and well, or no, all wrong, sorry. This is the student T with a single degree of freedom. You know, look, it has the heavy tails, so it decays much more slowly than the others. And then with nu equals 30, this is already, you know, more or less a Gaussian. Okay, and so the student T in the plot here corresponded, in the top plot there, corresponded to the green line. This was a and now the Hyperlaplacian. No, that's not correct actually. What we see here is that the red line, it decays linearly. So this is not a student, this is e to the minus gradient. Okay, because it decays linearly in this logarithmic space. So the Laplacian is like e to the minus norm of x. And then in this paper they advocate the Hyperlaplacian, which has additional parameters. And also a scale parameter that I'm not writing here. And they say the typical values to use for natural images are in the order between 1/2 and 4/5. Okay. So the argument that can be made is that if we construct a prior on intensities or on differences of intensities, so on increments, that they should not follow a Gaussian distribution because it is a poor match to what we observe empirically. Instead, we should use other functions. And this is what happens in the field of experts model. So to introduce it, I will rewrite our trusty old Gaussian model. So it depends on the vectorized latent variables x and our vectorized observations O. And yesterday I had rewritten this graph Laplacian in a different form, namely as a summation over all adjacent nodes in my graph. Here I'm using the unweighted version. And so we saw that our prior penalizes differences between the latent variables in adjacent nodes. Yeah, it doesn't matter. Okay. Good. And if I now want to bring back in these finite differences and so on, then I can rewrite it as follows. We can first make the distinction between the horizontal neighbors and the vertical neighbors. And I'm now saying here that this potential function rho is just its argument squared. So this here was for the right neighbor. This was for the left neighbor. And in a 2D image, we will have another term for the top neighbor. And we will have another term for the bottom neighbor. And then we have our data term. Okay, it's just a rewrite of this Laplacian in a different form. And so the finite difference, I can evaluate it by convolution with a +1 -1 mask. And this +1 -1 mask, I can encode this in a circular matrix, which I'm going to call here F1. So this is F1 times X, and if I want the result at a single pixel, then I only want the ith element of this. So the argument here of my operator rho, I can write, I had one filter for the right neighbor, I have a second filter for the left neighbor, and then further filters for the top and bottom neighbor. So, and then I can write this as a sum over my filters j, sum over my pixels I, plus the data term. So this here was the sum over the pixels, or the nodes, and this was the sum over the filters. So I have only rewritten this standard Gaussian Markov random field. So it's not even conditional. Okay? And now comes the generalization. So now we generalize to rho being something different than a parabola. And we also have the freedom to take a different rho, different potential function for each filter. So my new energy function, sum over filters, sum over pixels, but now I have a different rho for every filter. Okay, so the generalizations are the nature of the rho itself and the fact that we have a different rho for each and every filter. Now for the precise choice of rho, it could be you can really take anything you like. For example, the original authors, those were Stefan Roth, who is now a professor in Darmstadt, and Michael Black around 2007. They proposed the following. They said the energy should be this. Okay, and if you compare this to the log of a student t-distribution, so the log of a student t-distribution is minus log of 1 plus x squared if we have a single degree of freedom. So we're taking here a sum of logs of student t-distributions, or if we exponentiate the whole thing to obtain a probability, this would be products of student t-distributions that we use as a prior. Okay, now we have parameters, namely the parameters f and these parameters alpha. Those need to be learned. And again, we can, so f is a matrix holding a convolution operator. We could learn every coefficient of that convolution operator, or we can represent this convolution operator as a linear combination of some basis set of filters, and then we learn those expansion coefficients. Okay, and that is already the field of expert models plus data term. So this is the data term for image denoising. So it's not conditional. My filters f do not depend on O, but it is higher order. And how higher order depends on the size of my convolution stencil. So for example, let's take the simplest possible mask. Let's take a filter which is 1, 1, 1, 1, let's say. Then, because I take the logarithm, so if I do this explicitly, then I would have a term log of 1 plus xi plus xi plus xi plus 1. This is the right neighbor. Now I need the bottom neighbor, which is I plus the number of pixels in a row. I'm going to call this capital P. And then the one in the bottom right is I plus the number of pixels in a row plus 1. Okay, and this can no longer be written as a sum of functions over just two of these variables. So in terms of our famous picture, we are used to having these factors. And now this is no longer true. Now we have a factor that depends on 4 random variables at a time, the smoothness factor. And if my filter mask is bigger, or if my filter mask has more non-zero elements, then I shouldn't have written capital F here. I should have written small f, and capital F is the matrix representation of that. So if I use a bigger convolution filter, this corresponds to using factors with even larger scope. So what I have now is a higher order Markov random field over continuous random variables. Do you have questions? So these two changes on the basic theme of a Gaussian random field have made for huge improvements, and this is the work from 2007 and following. And now I want to tell you about the latest chapter in the story. These are trained, so the authors called it trained reaction diffusion processes. And it is by Chen and Wu and Pock from 2 weeks ago. And this is my personal favorite paper from this huge conference. So it's close to 3,000 participants. I forget how many papers, probably around 1,000, maybe a bit less. It's the best conference in the field, so it has a rejection rate of around 80%. And I like, so you will see in a moment that it's closely related to the formalisms that we've seen before, but as far as I know, it is the current best method in the world for image denoising. And so as a teaser, let me show you a few images. So Thomas Pock was kind enough to send me his slides, and I want to show you what you can do with these. We will only talk about the denoising scenario. So I will actually try and zoom in a little so you can see this on the beamer. So we have a noisy image, and this is the first step in this several step process. And actually, for those who know about image, or who have seen image processing algorithms before, this is it looks similar to anisotropic diffusion in the sense that it strengthens these orientations. It also invents some patterns where there are none, but actually this is corrected for in some of the subsequent iterations. Then here, this can actually also be used for super resolution. So you can turn this image into that image. And it can be used for JPEG deblocking. So here is the bad image. There is the less bad image. And on the screen where I have better contrast, the difference looks more impressive than on this beamer with too much light in the room. And since I'm showing images, let me show you a few more. So for example, here this image super resolution. I found this example pretty impressive. Huh? So this is the first one is what you get with so left is the input, right is the output. What you see here is a standard linear operator, and it blurs the edges. And here's the result of this new algorithm, which is really quite compelling. Now, if you compare it to the original, there's of course a minor difference, but some of the high-frequency texture, of course, must get lost in the downsampling process, and this cannot be recovered. But compared to the linear interpolation, this is really very, very good. Yeah, and as I said, in terms of image denoising, it's now better than anything that has been known before, and people have been working. There has been a huge amount of effort in this community. So let's look at these numbers. This is for a noise level of 15 and of 25. And here are, for these two noise levels, the best known methods. And you see that if they use a fairly large filter size, so 2, 5, and 8 are the number of iterations that they use. And you see that if they run the large filter size and if they take 5 or 8 iterations, then they are better than any of these methods, which include deep nets and heuristic methods and probabilistic methods and refinements of the methods that we've seen earlier today. Yes?
And what does this number mean, this 31.4?
Okay, the number itself is the peak signal-to-noise ratio. It is a quality measure, so higher is better. Yeah? And for sigma, you can always ask. For sigma equals 25, you also see that for 5 and 8 iterations, they are better. And I hope there's a table with the runtimes also. Yes, you see that some of these methods on larger images, they get expensive to a point where you don't want to run them on even bigger ones. I assume these are runtimes in seconds. And here is their method, which is really very, very fast. I don't know what these other numbers are. It's maybe CPU, GPU implementation, I'm not sure. So bottom line, it's super fast in prediction, but it's also relatively fast in training. Okay, now so there was a lot of advertisement, so let's talk about the actual method. So after training, so once we have the parameters of a field of experts, we can find its optimum for the latent variables by gradient descent. So I am copying down the formula we had before. The data term is again the one we want for denoising. And now I'm writing this in a slightly different form. Namely, I'm going to use my vector row here on, I'm giving it a vector argument, so I'm saying row j takes as input fj times x. So x is n by, one is n by 1, yeah. Fj is n by n, so this entire thing is n by 1, and then this thing is still n by 1, and we wanted to sum all of these up. So I'm taking the product with a vector of ones. And now we take the derivative of this with respect to x to descend towards its minimum, and this gives me, so fj transpose here is the inner derivative, and then I have rho j dot is the derivative of rho with respect to x. There we go, and then we have the derivative of the data term. Okay. And now we can do descent versus the optimum by saying x new equals x old minus magic step size times this derivative. Okay, and now we will use two modifications. To the standard field of experts. Namely, one is we initialize, so x0 is just the observations. We use only a finite number of gradient descent steps. We use script t gradient descent steps, and this script t is a small number. So here they've used something, between 5 and 10, or they show experiments between 5 and 8. So we don't go all the way to the minimum. And secondly, in each of these gradient descent steps, you use a different potential function and filter. So we use t different filters. So these filters now get an extra index, fj of t, and so-called flux functions. This was the row dot. Which the authors also denote with a phi. And this now also gets a superscript t. So, you know, this is of course one way to inject more degrees of freedom into your procedure. So you know, this allows us to tweak it even better to serve its purpose. But you can also look at it somehow as, you know, a prior that changes over time, yeah, which is a funny thing. Okay, and then the gradient descent step would look as follows. So xt plus 1 equals xt minus a magic step size times the derivative here was xt minus o plus t transposed and then this flux function phi j of t, which depends on fjt times x. Okay, and actually this x here can be omitted because I can absorb it, you know, in the other x that I have in this formula, in this one, and the mu can also be omitted because I can factor mu into these filters or into the flux functions that I'm learning. Okay, so I'm simply deleting these two here. Okay. So this dependence on time is now here in the flux functions and in the filters. And this is once I have learned all the parameters. So the parameters that I have are my filters jt and my flux functions jt for all j and t. And they've used something like between 25 and 50 different filters and around, you know, below 10 steps in this process. Yes?
I think there should be a minus in front of the observation.
It's x minus o. Yeah, thank you. Okay. Good. Now again, usually they are not represented in terms of individual coefficients, but f in their case is represented in a basis of DCT functions, discrete cosine transform functions, and phi, which is a one-dimensional function, is represented in a basis of B-splines or radial basis functions. I can show you a picture in a moment. So now how do we find the parameters? The training of this. We can think of the training either as an optimal control problem on a partial differential equation, or we can think of it simply as gradient descent. So we want to find those parameters. We want to optimize over the filters f and these flux functions, and we have a total of m training images. So this is the sum over the training images, and we are training this just for the denoising scenario now. We have a sum over training images, and then I want to make this squared error of my final estimate. So xm script t minus the ground truth, which I should call maybe m, so this is the ground truth and this is the final estimate. I want to make this as small as possible. Subject to the following conditions. So I initialize my xm 0, so this is a 0, not an observation, by my observation. O, I should latex this. And then I want the intermediate steps of this process to end, well, to give me my final result. So xm t plus 1 equals xm t, and now this is the same formula as above, minus sum over j fjt transposed phi jt fjt xmt plus the observation, and this must hold for all times from 0 up to t minus 1. So there is our so-called optimal control problem. Because we fix a start point. This is here. And now we want to evolve this start point by, in terms of this evolution equation, into an endpoint, which you see here, into an endpoint which is as close as possible to the desired output. And optimal control problems, of course, this is something that our colleagues here at IWR study a lot. But you can also, think of this differently. You can turn this into an unconstrained optimization problem. By unrolling these constraints in the objective of our optimization problem. So in other words, we replace x script t by this expression here, and so this in turn depends on xt. So we now insert this equation again in those, and so on. And so if you do this for 10 time steps, you get a pretty formidable expression, but unconstrained. And so we now have an objective that depends on the parameters f and phi. And now we differentiate this and do gradient this step, or the authors use a quasi-Newton method to find the optimum parameters. So the expressions are very big, but ultimately the optimization strategy is a pretty simple one and relatively fast, as I said. So on hundreds of images, the training time is around a day on a big computer for quite a few parameters that we have here. And a day on a CPU, you know, it's not little, but it is faster than most convolution nets and so on that can be trained on a CPU. So this is what you have to compare it to. Okay, and all of this pays off in terms of performance, as I have shown you initially. There is so I introduced it in the framework of an extension to field of experts. The authors introduced this in a different framework. The authors explain this in terms of a reaction diffusion process which is learned. So both viewpoints are, you know, equally valid. I've used the one which is closer to the things that you've seen in this lecture. Now, as I said, this didn't win a Best Paper Award. This is my personal favorite from this conference. And I'm a little proud that, you know, we can treat this here. So, you know, this either tells you that image processing is really simple, if after the end of a one-semester course we can read the latest papers, or it can tell you that we've covered lots of ground, which is, of course, the interpretation I prefer. Okay, so to conclude, I show you pretty pictures of what they can do. Again, these are the slides kindly shared by Thomas Pock, and I think we will walk through this really quickly. So they introduced this in terms of a different framework, as I said, namely anisotropic diffusion, and show the similarity between these, and mention relation to fields of experts. And this is the reaction diffusion equation. Yeah, so the data term is can be seen as a reaction term, and the prior can be seen as a diffusion term. And all of this is made time varying. And this is a picture I much like. I jested a little with Thomas when I saw his poster that this is what he needed to get it accepted at the conference, because these days, you know, neural networks are very fashionable. And yes, you know, so he was laughing that yes, this can be interpreted as a convolutional neural network. It's a little different from standard networks in the sense that we have not one but two convolution operations. Yeah? So there is a convolution also after the nonlinearity here. If it wasn't for the time dependence, this would be a recurrent network. And maybe, you know, if you have very little training data, maybe that is also an interesting thing to do, to not make all these filters time dependent, but use the same ones throughout. Then you have a recurrent network. Another difference is that here they obtain at each layer just a single output, which is then used as input for the next layer. In principle, you could have multiple outputs here and then take a nonlinear combination of these, or take a combination of these as the next layer. This is what I mentioned, how these functions are represented. So these are, for example, these flux functions phi, and rather than learning them, you know, coefficient by coefficient, they are here shown as, or they're expanded in a radial basis function on the left-hand side, or in a function of these triangles on the right-hand side. Yeah, so what we see on the left-hand side are just Gaussians, which are spaced by a predefined distance, and the only thing we learn is the amplitude of each of these Gaussians. And then taken together, they can represent functions like the black one that you see here. Okay, and this is how they parameterize their filters. So you don't learn them coefficient by coefficient, but expand them in a discrete cosine transform basis. And then this is the optimal control learning equation that you've seen. Here are some of the functions phi that are being learned. Here are some of the filters that are being learned. And now this is nice to look at. We see here the original image, and then step by step. This is the first step. This is the second step. Am I forwarding or not? No. Now. Okay, and you see that after the first step, the changes are pretty slight, but still you need them if you want to beat the previous, worldwide state of the art, as we've seen. Yeah, it depends on the number of iterations required. And then the final result is this. So the method discovered only noise down here, and so this was blurred completely. It probably invented a little bit of texture in the grass, but it actually retained the truly present texture here in the tree trunk and in the leaves. Yeah, so let's go back a few steps. The initial image was this one. And the method learns to distinguish between true edges, which are maintained, and the edges just resulting from the noise in otherwise homogeneous region, which are removed. Okay, you see that it keeps getting a little bit better over iterations. We argued that it's fast and that it's good, and those were the super resolution results that you've seen. And here's another JPEG deblocking result, which I think is pretty impressive. Okay, with that, with those pretty pictures, I want to end today.